Hi, my name is Simone Faro. I am Associate Professor at the University of Catania, Department of Mathematics and Computer Science, and I am going to present a paper in collaboration with Domenico Cantone from the University of Catania and Arianna Pavone from University of Messina. In this paper we investigate the approximate string matching problem when the edit operations are non-overlapping unbalanced translocations of adjacent factors. String alignment and approximate string matching are two fundamental problems in text processing. In recent years, much work has been devoted to the development of efficient methods for aligning strings, and despite sequence alignment seems to be a well-understood problem, especially in the edit distance model, the same cannot be said for the approximate string matching problem on biological sequences. Formally, given two input sequences x of length m and y of length n, the string alignment problem consists in finding a set of edit operations able to transform x in y, while the approximate string matching problem consists in finding all approximate matches of x in y. The closeness of a match is measured in terms of sum of the costs of the elementary edit operations necessary to convert the string into an exact match. For example, if we consider the pattern x and the text y as depicted in figure, we can locate three distinct occurrences of x in y, here depicted in red. The first one is an exact match, since x appears in y with no changes. The second occurrence is an approximate match, since the character c, depicted in blue, must be edited to obtain an exact match, and specifically it must be changed with a t. Finally, the last occurrence needs another kind of editing to obtain an exact copy of the pattern. We have to swap, indeed, the two adjacent characters a and t depicted in blue. Most biological string matching methods are based on the Levenshtein distance or on the Demarest distance. The edit operations in the case of the Levenshtein distance are insertions, deletions, and substitutions of characters, whereas in the case of the Demarest distance, swaps of characters are also allowed. Both distances assume that changes between strings occur locally. However, evidence shows that in some cases large-scale changes are possible, and that such mutations are crucial in DNA, since they are often cause of genetic diseases. Inversions, for example, are large-scale mutations of a DNA sequence, where pieces can be retrieved in reverse order. The string y, depicted in future, can be easily transformed in the string x if we allow an edit operation of the string where the entire factor depicted in red is reversed. In a translocation, for example, large pieces of DNA can be moved from one location to another. Translocations can be balanced when equal length pieces are swapped, or unbalanced when pieces with different lengths are moved. Interestingly, unbalanced translocations are a relatively common type of mutations and a major contributor to neurodevelopmental disorders. Hence, the need for practical and efficient methods for detecting and locating such kind of large-scale mutations in biological sequences arises. For example, if we consider the pattern X and the text Y as depicted in figure, we can locate two distinct occurrences of X and Y, here depicted as underlined subsequences of the text. Factors involved in any translocation are depicted in red and blue, respectively. The first match involves a single translocation of two factors of length 7 and 2, respectively, while the second match involves two translocations. In the last 3 decades, much work has been made for the alignment and matching problem, allowing for chromosomal alteration, especially for non-overlapping inversions. This table shows the list of all solutions proposed over the years, together with their worst case, average case, and space complexities. Regarding the approximate string matching problem, a first solution was presented by Canton et al. In 2011, where the authors presented an algorithm running in quadratic worst-case time and m-squared space for the approximate string matching problem, allowing for non-overlapping inversions. Additionally, they also provided a variant of the algorithm which has the same complexity in the worst case, but achieves linear time complexity on average. Canton et al. Also proposed in 2010 an efficient solution running in an m-squared time and m-squared space for a slightly more general problem, allowing for balanced translocations of adjacent factors besides non-overlapping inversions. The authors proved their previous result in 2014, obtaining an algorithm having a linear time complexity on average. In this paper, we investigate the approximate string matching problem under a string distance whose edit operations are non-overlapping unbalanced translocations of adjacent factors. To the best of our knowledge, this slightly more general problem has never been addressed in the context of approximate pattern matching on biological sequences. First, we propose a solution to the problem, based on the dynamic programming approach, which needs n m-cubed time and m-squared space. Subsequently, we propose a second solution to the problem that makes use of the directed acyclic word graph of the pattern and achieves an n-log squared time on average for alphabet of size sigma greater or equal to 4, still maintaining the same complexity in the worst case as in the first solution. First, we present a general dynamic programming algorithm for the pattern matching problem with adjacent unbalanced translocations. Our algorithm is designed to entirely compute for any position j of the text all the prefixes of x which have a match with the suffix of y of length j, by exploiting information gathered at previous iterations. Since the translocation involves substrings of the pattern x, it is useful to consider the set fjk of all the positions in the pattern at which an occurrence of the suffix of yj of length k ends. For example, if we let x and y as depicted in the slide, then f5 is the set of all positions in x at which an occurrence of the suffix y5 of length 3 ends, namely cat. Thus, f5 is equal to the set containing 3, 7, 13. Similarly, we have that f5 is equal to the set containing 3, 7, 10, and 13. Observe that f5 is a subset of f5. The set fjk can be computed by way of a recursive relation. Specifically, fjk can be computed by means of the fact that I belongs to fjk if and only if one of the following conditions holds. The first base case occurs when the character of position I in the pattern is equal to the character of position j in the text, and the k is equal to 1. The recursive case occurs when the character of position I in the pattern is equal to the character of position j in the text, and I-1 belongs to fj-1 k-1. Additionally, if we observe that fjk is always a subset of fj k-1, we can represent the set fjk by means of a single matrix F of size m times n, where we set fij as the length of the longest suffix of xi, which is also a suffix of yj. Thus, we have that I belongs to fjk if and only if f of I and j is greater or equal to k. In addition, we also introduce the set of matching position pj for each position j of the text as the set of all values I such that the prefix xi of the pattern has a match ending at position j of the text. Thus, the pattern has a match ending at position j of the text if and only if the value m belongs to the set pj. If we consider the strings x and y as depicted in figure, we can easily see that p2 is the set containing the value 2, since the prefix of the pattern of length 2, namely ca, has an approximate occurrence ending at position 2 of the text, namely ac. Similarly, p4 is the set containing the values 1 and 4, since the prefixes of the pattern of length 1 and 4 both occur in the text ending at position 4. In this example, the pattern has 3 approximate occurrences ending at position 4, 8 and 10 respectively. The set pj can be also computed by way of a recursive relation. Specifically, we have that I is in pj if and only if one of the following two facts hold. The first base case occurs when the character of position I in the pattern is equal to the character of position j in the text, and I-1 is in pj-1. The second recursive case occurs when we have that, for some k and h, we have that I minus k is in fjh, I is in fj minus hk, and I minus k minus h is in the set of matching values for the position j minus k minus h. In this context, the second condition refers to a translocation of adjacent factors of length k and h, respectively. Based on such recurrence relations, a general dynamic programming algorithm can be reconstructed. Here we present the pseudocode of the resulting dynamic programming algorithm, called algorithm 1. Due to the 4 for loops at lines 2, 4, 9 and 10 respectively, it can straightforwardly be proved that algorithm 1 has n m cube time and m square space complexity. Indeed, the matrices F and P are filled by columns, and therefore we need to store only the last m columns at each iteration of the for loop of line 2. We now present our second solution obtained by improving the first algorithm by means of an efficient method for computing the sets fjk. Such method makes use of a function named endPos function and of the Dauge of the pattern x. Specifically, for a factor w of a string x, we denote with endPos of w the set of all positions in x at which an occurrence of w ends. For example, if we assume x is a string of length 9, as depicted in figure, then we have that endPos of ag is equal to the set containing 2, 5 and 9, since the substring ag occurs 3 times in x, ending at position 2, 5 and 9 respectively, in that order. Similarly, we have that endPos of gcc is equal to the set containing the value 7. The Dauge, or directed acyclic word graph, of a pattern x is a deterministic automaton whose language is the set of factors of x. For each position j in y, let w be the longest factor of x, which is a suffix of yj. Also, let qj be the state of the Dauge, which is reached by scanning the string w starting from the initial state of the automaton, and let lj be the length of w. We call the pair qj-lj a y configuration of the Dauge. The idea is to compute the Y configuration QJ-LJ for each position j of the text while scanning it. The set fjk, computed at previous iteration, do not need to be maintained explicitly. Rather, it is enough to maintain only Y configurations. These are then used to compute efficiently the set fjk only when needed. In this slide, we show the pseudocode of procedure Dauge delta, which is the Dauge state update algorithm which is used for computing the new Dauge configuration after scanning a single character of the text. Let x and y a pattern and a text as depicted in figure. Here, we show also the Dauge of x, where its edges are depicted in black, while suffix links are depicted in red. Observe that after scanning the suffix y5, starting from the initial state q0 of the Dauge, we reach state q2 of the automaton. Thus, the corresponding Y configuration is q2-2. Similarly, after scanning the suffix y11, we get the Y configuration q4-3. For the computation of the sets fjk, we also need to introduce an additional function, phi, which takes as input a state q and a length key, and computes the first node p in the suffix path of q such that the length of the suffix link of p is less than key. Then, to compute the set fjk, we take advantage of the fact that fjk is equal to the endpos of phi of qjk. Thus, the time complexity for the computation of phi q key can be bounded by the length of the suffix path of node q, and specifically, since the sequence of the length of the nodes in the suffix path from q is strictly decreasing, we can do at most len of q iterations over the suffix link, obtaining a linear time complexity in the size of the pattern. Observe that if we proceed for decreasing values of h, the sets fjh can be computed in constant time from the set fjh plus 1, with at most one iteration over the suffix link of the state phi qj h plus 1. The resulting algorithm for the approximate string matching problem, allowing for unbalanced translocations of adjacent factors, which is named algorithm 2, is shown here. For computing the worst-case time complexity of the algorithm, we consider the following facts. The main for loop at line 4 is always executed n times. For each of its iterations, the cost of the execution of Dauge delta for computing the new Y configuration requires at most m time. Since we have that the cardinality of pj is less or equal to m plus 1, the for loop at line 7 is also executed m times. In addition, since we have Lj is less or equal to m, the two nested for loops at lines 11 and 14 are executed m times. Observe also that the transitions of suffix links performed at lines 12 and 15 need only constant time. Thus, at each iteration of the main for loop, the internal for loop at line 14 takes at most m time, while the for loop at line 11 takes at most m squared time. In addition, the for loop at line 16 takes at most m time, since the cardinality of pj minus h minus k is less or equal to m plus 1. Finally, the tests at line 17 can be performed in constant time. Summing up, algorithm 2 has an n m cube worst-case time complexity. Regarding the space complexity of the algorithm, in the preprocessing phase, the Dauge of the pattern, together with the associated endpost function, is computed. Since for a pattern X of length m we have that the cardinality of the set of the states of the automaton is less or equal to 2m plus 1, and the cardinality of the set and pose of q is less or equal to m for each state q, we need only m square extra space. We also present a detailed analysis of the average case complexity of the algorithm, and from such analysis it turns out that our automaton-based algorithm has an n log square m average time complexity if we assume that the size of the alphabet sigma is greater or equal to 4. You can find all the details in the paper. That's all, and thanks for your attention.